Welcome, it's David Kearns here with another With a Sharpie video. This follows on from the last two videos which covered the topic of carbon capture approaches. So first off talking about what carbon capture is and then talking about different types of carbon capture. We called them post-combustion, pre-combustion and oxyfuels. This session is going to be about what is termed carbon storage, or more accurately carbon dioxide storage. And why do we need that? Well, if you look at the carbon capture videos that I produced previously, essentially what we had is we had some sort of system which was what we call capturing CO2. We'll call this a capture plant. And the purpose of a capture plant is to produce a high purity CO2 stream. So often the CO2 that we get from industrial processes like power stations or cement works or aluminium smelters is dilute. The CO2 is dilute. It's mixed with a lot of other things. And so by using a capture plant, we can purify it to high purity CO2. But of course, if we just let that CO2 go straight back into the atmosphere, well, it's a pointless exercise. We ultimately need to find a way to safely store this CO2 away from the atmosphere and away from where it can have an effect on the greenhouse effect. And so there's a few different ways we can do that, and that's what I wanted to talk to you about today in carbon storage. So the first one, and one that gets a fair bit of attention, is, so where does this go? This goes off to storage. The first one is something known as Geo Sequestration. So what does that mean? Geo means earth, sequestration means storage, so storage in the earth. And that can happen a few different ways, but essentially what it involves is taking this high purity CO2 stream, pressurizing it to a really high pressure to something we call supercritical CO2. That just means it's really high pressure. And ultimately inject it into the earth in one form or another. And so that can be done in a few different ways. The first one that has probably got the most history is something known as enhanced oil recovery, or EOR. That basically involves injecting it into oil wells. So this is the oil that we produce for refining into petrol and diesel and so on. If you inject CO2 into oil wells, what you can do is help push out remaining bits of oil that were in the ground that previously wouldn't come out on their own. So essentially it's a way of extracting extra oil, which is very good from a commercial perspective because basically we're finding a commercial use for this CO2. The oil that we get helps to pay for recovering for injecting CO2 into the ground, which is good. The downside, of course, is we're producing more oil, which people are going to combust somewhere, and that's just going to make more CO2. It's not really getting to the root of the problem. The second approach is to use it's sort of a variant on this, is disused oil and gas wells. So we basically take oil and gas wells that have already been drilled, have already been used up, and so there's no really sort of commercially recoverable oil or gas anymore. And we inject our CO2 into those. So that's got the advantage that a lot of the cost has already been absorbed. So drilling is an expensive thing to do. Someone's already paid for that. They're not using it anymore, so let's use it to store some CO2. So the downside is that you're not getting a commercial return. You're not actually getting paid for injecting CO2 into the earth under this approach. Whereas if you were doing enhanced oil recovery, the oil that you're recovering pays for it. And so this second approach, and indeed most of these subsequent approaches, don't really work without a price on CO2 emissions. If you don't have some form of ability to be paid for reducing CO2 that goes to the atmosphere, these things aren't economic. And the third one is known as using what are called saline aquifers. So what's a saline aquifer? It's basically a brine or salty water, if you like, that sits in certain geological formations in the earth. So if I was to draw you sort of a diagram, here's the surface of the earth, and underneath the earth we've got basically these big saline aquifers which kind of sit in all kinds of weird and wonderful formations under the earth, usually capped by some kind of bedrock or some kind of material that locks them down. So, and I'm not a geologist, so I'm sure the geologists who are watching this could correct my somewhat simplistic understanding. But essentially we've got this aquifer that sits under the ground. It's not fresh water, it's not usable by humans. And the nice thing is that that's essentially a location where we can get our drilling operation, and we can drill our well down into this. We can take our CO2 stream, and after we've drilled our well, we can inject that down, and essentially the CO2, because it's lighter than the water, tends to float up and will fill these spaces near the top. So that's got some advantages. There's a lot of saline aquifers around the world. It's a viable option. One of the disadvantages is that this is still very much a work in progress in terms of human understanding. Saline aquifers we don't have a lot of history of interacting with them or doing things with them on an industrial scale. We've known about them for a long time, but they weren't really useful to us. So there's still a lot of work going on about testing this approach and seeing how viable it is. And there are other sort of variants on this approach where you can inject into other kinds of rock formations in the ground that could store CO2 as well. The main thing is that they can cap them off. They have some sort of bedrock or non-permeable rock. The CO2 can't penetrate it, so it gets bottled up. So what are some of the advantages and disadvantages of geosequestration? Well, the first one, and it's a pretty obvious one, is that you can get paid, especially if you're using enhanced oil recovery. So if you're using your CO2 to actually extract oil from the ground, that's fantastic in terms of financial returns. I guess the second advantage is that you end up with stable storage locations, or at least that's the idea. You pick geological formations that are stable. So that means that you can lock the CO2 away, which is ultimately the entire point of CCS, is stable storage locations. But a key disadvantage is you might get leaks. So obviously it's either stable or it leaks if you don't get it right. So there's a lot of geology and a lot of research and a lot of testing and modeling required to make sure that you don't get leaks. And secondly is safety, which is related to leaks. If you get large-scale leaks of CO2, essentially that can kill people. It can asphyxiate people. There have been natural CO2 releases from volcanic activity in the past, which have actually killed large numbers of people because the CO2 basically displaces oxygen and means people can't breathe. Because there's dangers of leaks and particularly dangers of safety to humans, that's something really to concern yourself about. A second approach to geosequestration is what's known as mineral storage. So this is basically the idea of we take some CO2 from our carbon capture plant, we put it through a reactor, and out of this we produce a solid material. So it's a solid, we call it mineral storage. It's really a mineral-like storage because it's an artificial material. So how does that work? Well, basically what we do is we take what are known as metal oxides. So it's essentially any metal atom attached to an oxygen atom. We add CO2 to that in a chemical reaction, and we end up with a metal, what's known as a metal carbonate. And for those of you who like to see equations, an example might be we take something like calcium oxide. So as I said, calcium is a metal attached to an oxygen atom. We add the CO2, and this makes something known as calcium carbonate, also known as calcite. This is a naturally occurring material. It's the bulk of limestone. So when you see limestone, limestone is mostly made of calcite. This has got a few very key advantages. So advantage number one is obviously it's stable. You know, you've made a material that is a solid material. It's no longer floating around in the atmosphere, having an impact on the amount of heat trapped near the surface of the Earth. So it's very good from that perspective. I guess we do have to think about disadvantages, and in this case, a key disadvantage is that it's still a work in progress. So people are very excited about this, but it hasn't really come along very far yet. It's not anything like large-scale commercial application just yet. Oh, and sorry, a second advantage is that you can actually produce useful materials. So some people are looking at making mineral storage materials that could actually be used, say, as components of concrete, or maybe road bases or things like that, and actually can substitute for natural materials we currently use. Now, the thing is, these kinds of reactions, making metal carbonates, do happen naturally. So they happen in the environment on their own. They actually are a net producer of energy. They actually give off a little bit of heat when they happen. The trouble is they happen very, very slowly. And if we want them to happen rapidly, which is what we're going to need if we want to produce mineral storage on an industrial scale, we actually need to put catalysts and or heat in. And so that can, there's a cost disadvantage here, that you basically have to spend money to convert things to calcite or whatever other kind of mineral you're interested in. But look, it's very promising. It's something that I hope we get some serious breakthroughs in. If we can get the industrialization of this process, get it out of the pilot plants and into industrial scale, and if we can keep these costs to a minimum, that will be a very exciting development for carbon storage. So that's it for today. I hope you learned something about a few different types of carbon storage. This has been David Kearns. You have a good day.